So what about the other functions? And there will be times where you will have to find the error of a sine function or a tangent function, right? Well, you know what? The rules don't really apply, right? What you probably do is there's going to be a maximum value for x. So this is going to be probably just the x value plus the uncertainty. There's going to be a minimum value for x, which is going to be just the value of x minus the uncertainty, right? And you plug them in, and you're going to have a maximum value for a certain value x, right? And a minimum value for the same x. Subtract, divide by 2. This is your uncertainty of the function, right? You don't have to know how to do it, right? The real way to do this can be very complicated. It has a lot of different theorems to it. But you know what? It's not really necessary. Find the maximum minus the minimum, divide by 2. That's all you do. So these, I don't really have to teach you, right? What you have to do though is just input the maximum minimums and find the difference and divide by 2. Okay, now that we have that done, graphing is also an important part of the IB. You see this graph, you have values, right? You have centimeters here, you have force here, and you're graphing. And what you do is, well, every point has a certain amount of error. This measurement has a plus or minus, right? So many amount of centimeters. In this case, it looks to be that it is plus or minus 0. What is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0.1 centimeters, right? Because it looks to be that this is one grid wide. And this is just for the x-axis. The y-axis, this one, let's put it a different color. Let's put it in green probably. From here to here has an uncertainty of 0.2 newtons because one grid seems to be 0.2 newtons, right? So this is how you graph the error margins. Sometimes it's going to be different for every measurement. Sometimes it's smaller, sometimes it's bigger. But, you know, you just graph it, put it in the graph. And most of the times it's going to be a linear relationship. If it's not, you should try to make it linear. We call this linearization. This is also a mathematical method. Later on, when you do, probably at the end of DP2, right? We'll practice a lot of the paper 3, section 2. What happens is a lot of the students get a lot of those questions wrong, which are easy questions. The only thing you have to do is have experience. Once you try it once or twice, you know what you did wrong. When you try it again, you probably won't have the same wrong answers. Most of the questions are the same anyways, so once you try once or twice, it's very easy, right? Okay, this is how you put the error bars. This blue line is the line of best fit. The line of best fit most of the errors. So you should probably make it go as straight as possible through most of these centers as possible, right? If you go down, this is not a line anymore, right? The measurements are like this. This is not a straight line. You just put a curve as best you can through all the points. If you do an experiment, you probably have to use Excel or some other program to make this line for you. And there's mathematical methods for that. It's not very hard. You'll probably use this, or they'll probably teach you as you do the experiments. Okay. Now, if you're looking for the slope, right? The slope is also going to have a certain amount of error. So if you calculate the slope from this point, actually let's put a different color. This blue, red, let's put orange. So this point has a value, this point has a value, right? The line of best fit is you want to just go through the centers, right? So first of all, let's calculate the slope. What is the slope here equal to? And if we can't really see the values, let me put the coordinates. Here is 1, 2, 3, 4, 5, right? So it's going to be 3.5, and the height is 7. Here is 0, 0, right? So the slope is probably going to be 7 divided by 3.5 plus 2. This is your value for slope. We take this as the average. One big question is, well, what is the maximum slope? What is the minimum slope? The maximum slope is going to be the green line. Right? So if you see this maximum slope, let's zoom in. It's going to be the line, the green line, that best goes through every single one of the error bars. Right? So you start off here, right? And you start off here, and you kind of tweak it so that it enters every single one of the error bars. So you can see here that this error bar and this error bar is what pushes it up a little bit, so it goes through here, right? It can go through here as well, no problem. So there's one point, and then there is this other point in green. And these 2 points more or less go through all the vertical bars, error bars, right? Let's make this still 0, and then it's negative 0.2. Here in the top is going to be still 3.5, but now it's going to be 7.2, right? It's still inside the error bars. So now it's going to be 7.4 divided by 3.5, right? What is this? Using a calculator? Yeah, 2.1-ish, right? Let's do the same for the red slope. The red slope is probably the minimum. So you can see it crosses the bottom here, right? And the top here, more or less. So it's the minimum slope. This is equal to, well, let's look at the coordinates. It's going to be 3.5, comma 6.8. And here it's going to be 0, comma 0.2, right? Therefore, it's 6.6 divided by 3.5, and that is going to be 1.9. There's 1.9. So what is the error in the slope? The error is the maximum, 2.1, minus the minimum, minus 1.9, divided by 2. So the slope error is going to be 0.2 divided by 2 equals, right, 0.1. This is your error. You have to have units. What do you think are the units for the slope?
F over x.
Wow.
No, n over 7.
Yes. So we divided f by x, right? But these are not the units. The units are n and centimeters. So the units for this are newtons per centimeter, right? You probably want to change this into SI units, so it's probably going to be, what happens when we change centimeters to meters?
0.1.
Yes. So it's 0.00, sorry, 001, right? Isn't it? 1/100th of a meter? Newtons per meter. Right? Okay. That takes care of slopes, and that also takes care of uncertainties. So is there any questions about this? Okay. This isn't very common. This is only used in lab experiments, and it's only used in a small section of paper 3.